Okay, we now move on to the third objective in section 8.3. The student will be able to construct probability trees. So we did the conditional probability A given B is probability A and B divided by probability of B. And then we used a product rule, probability A and B is probability of A times the probability of B given A. And now we're going to use trees, probability trees, things you can see. And then next time we'll talk about independent, dependent. Two machines are in operation. Machine A, which produces 60% of the items. Machine B produces the remaining 40%. Machine A produces 4% defective items. So 1 minus that, 96% are good. Machine B is not quite as good as Machine A. 0.05 or 5% defective, 95% good. An item is chosen at random. And so we want probability that the thing is defective. Probability defective. Well, you can see from the tree and just from reading that there are two ways that we can have a successful, so to speak, so-called successful event of being defective given this situation. You can be defective having been produced by machine A, or you can be produced by machine B and be defective. Two different ways to do it. So it's an or problem. Okay, so that's significant, right? Or probability A or B. That means we're going to use an addition rule. Okay, probability A or B. And so because the events are mutually exclusive, you cannot be both from machine A and from machine B. We're just going to add the two probabilities to get probability of defective. You could be machine A and B defective, machine B and B defective. So we're going to add probability of A and defective to the probability of B and defective. Now, product rule, okay, multiplication rule, probability A and D is the probability of A times the probability of D given A. And we know those probabilities. This one, probability of B and D, is probability of B times probability of D given B. Probability of A, well, A is used 60% of the time. So 0.6. And probability of D given A means the likelihood of being at this node right here. Now, think about that. Probability of D given A, that means that you have to clear the first hurdle of having been produced by machine A, and then at that point you have to go on and be defective. So it's an and at that point, probability of A and defective, which you'd have to multiply the probabilities because of the and multiply the 60% and the 0.04%, right? These guys, they don't happen often. It's only 60% of 4%, which is a little more than 2% of the time you get machine A and defective. These happen a lot, 96%, 60% of the 96%, or 96% of the 60%, where of means times. That happens most of the time. These don't happen very much. That's 5% of 40%. These happen sometimes. So probability of A times probability of D given A. And then we're going to take two other numbers that we see, right? The 0.04, that's probability of B. That's right here. Times the probability of D given B. What's the probability of defective given that you were produced by machine B? And that's 5%. So that 5% is this 5%. Again, probability of A is this 60%. Probability of defective given A is this 0.04. Those get multiplied according to the formula and added to this product. And you run that arithmetic, and you are going to get this a little bit more than 2%, and this is exactly 2% for the second one, for a total of 0.044. 4.4% of the time you will be defective. In the preceding slide, we saw an example of a probability tree. The procedure for constructing a probability tree is as follows. Draw a tree diagram corresponding to all combined outcomes of the sequence of experiments. So first you had to come from a machine, and then you had to be either defective or not defective. Assign a probability to each tree branch, and all that was given in the paragraph, the problem that you were supposed to do. Probability that the occurrence of a combined outcome that corresponds to a path through the tree is the product of all branch probabilities on the path. So we saw two paths and two products, two multiplications, and then we added them because they were both successful outcomes, successful in the sense of being defective. So here's the situation. A new example. A coin is tossed and a die is rolled. So you got the coin, maybe a quarter, and then a die, a number cube, is rolled. Find the probability that the coin comes up heads and the die comes up 3. And so first you flip the coin and you have a head or a tail, and the assumption is that each happens with probability 0.5. Now, given that you had a head, the die could come up 1 or a 2 or a 3 or a 4 or a 5 or a 6. And the same is true if the coin came up tails. You have either 1, 2, 3, 4, 5, or 6. Probability of each of these outcomes is 1/6, assuming a fair coin. The outcomes for the coin, the sample space for the coin tossing experiments are HT, because you're only flipping it one time. And then 1, 2, 3, 4, 5, 6 for the die. Using the fundamental principle of counting, okay, multiplication Well, I guess we just have to call it the fundamental principle of counting. I call it the cafeteria problem. If you have the possibility of 2 sandwiches, 3 drinks, and 4 salads, then the total number of lunches possible is 2 times 3 times 4. In the coin tossing followed by die rolling experiment, it's 2 times 6, or 12 total outcomes of the sample space. And of course we have that for each of the 12 nodes at the far right of the tree diagram. 4, 5, 6, 7, 8, 9, 10, 11, 12. But of course it's just 2 times 6. Now the problem was find the probability of heads in a 3. Now there's that word and, right? There's that word and. So we're talking about intersection, head in a 3. And in this case we have, well, independent events. The number that comes up on the die has nothing to do with the head or tail that you got from flipping a coin. It's not like there's a dependence there, as if you have a without replacement situation. And so we're just going to multiply the simple probabilities. 1/2 for the head, 1/6 for the 3, 1/12, and you can see that it's 1/12 by looking at the tree. Head in the 3, we're talking about, okay, what's the probability of this path right here? Well, it only happens 1 time out of 12. But you could also get it by multiplying. Fundamental principle of counting. Now let's look at the same problem. Flip a coin, roll a die in a slightly different way. To find the probability of heads and then a 3, well, there's that and, right? That's what they said. Heads and a 3. Heads and then a 3. Well, probability of heads times the probability of 3 given heads. Now, given that you had a head, what's the probability of 3? Well, it's no different than if you had a tail. It's no different than if you didn't have a coin flip at all. It's just going to be 1/6. Now, the probability of getting a 3 on the die does not depend on the outcome of the coin toss. We say that these two events are independent, since the outcome of either of one of them does not affect the outcome of the remaining event. They have nothing to do with each other. They don't affect each other's probability. And of course, this was the 1/2 times 1/6, which is 1/12. We actually didn't even need this, did we? We didn't need given heads. We could have said 1/6 anyway.